Every click, swipe, and transaction we make generates data. We are producing information at a scale that single machines cannot ingest fast enough. For decades, the standard response was to buy a bigger computer. This strategy, known as vertical scaling, meant investing in expensive, custom-built supercomputers to handle the growing load. But hardware has physical and financial limits. There is a ceiling to how much processing power and storage you can pack into one machine before the heat, power requirements, and sheer cost become unsustainable. Overcoming this bottleneck required a shift in logic. Instead of building one giant machine, engineers began networking together thousands of ordinary, inexpensive computers, commodity hardware, and making them act as a single unit. To understand the mechanics of this shift, we've partnered with Royal Research to explore the software framework that made this distributed approach a reality, Apache Hadoop. Managing the data explosion required moving away from individual supercomputers toward a system that orchestrates thousands of cheap machines to share the burden. In a cluster of thousands of computers, the first challenge is organizing the files. This is the role of the Hadoop Distributed File System, or HDFS. HDFS slices massive files into uniform blocks, scattering them across the cluster. Commodity hardware inevitably breaks, losing stored data. But Hadoop expects this. It replicates each block across multiple nodes, instantly restoring data from backups if a machine fails. This replication creates fault tolerance. Even if multiple physical machines fail simultaneously, the dataset remains intact and accessible. Once the data is stored, the next challenge is processing it. Moving terabytes of data over a network to a central processor would create a traffic jam that brings the entire system to a halt. Hadoop uses data locality, sending processing instructions directly to machines holding the data. In the map-reduce-map phase, tiny instructions run in parallel, each node solving a small puzzle piece. Finally, the reduce phase gathers these decentralized results into a single answer. This parallel processing shifts the timeline of big data analytics. Tasks that would take weeks for a single machine to calculate are finished in minutes by the cluster. Managing thousands of independent machines processing data at the same time requires a digital traffic cop to maintain order. That role belongs to Yarn, yet another resource negotiator. Yarn allocates processing power and schedules applications across the cluster to ensure resources are used efficiently. Yarn provides the coordination necessary for thousands of separate computers to behave like one powerful, unified system from the user's perspective. This architecture changed the economics of computing. Because organizations could scale by adding off-the-shelf servers instead of purchasing proprietary mainframes, the cost of storing and processing massive datasets dropped significantly. Hadoop also provided the flexibility to handle different types of data. Unlike traditional databases that require strict formatting, Hadoop can ingest unstructured information like social media text or video logs in their native formats. As an open-source project, Hadoop's foundation supported a vast ecosystem of specialized tools. Projects like Apache Spark and Hive were built to plug into Hadoop, expanding what organizations could do with their data. This access to high-level analytics brought predictive power to sectors outside of big tech, empowering the world of finance, improving outcomes in healthcare, and transforming retail companies to utilize the data they were already collecting. Hadoop provided the distributed architecture to build the modern, data-driven world, establishing the blueprint for managing information at an impossible scale. Thank you for watching. We'd also like to thank Royal Research for supporting this look into the architecture of big data.